Hi everyone, my name is Zebin. Today I would like to introduce you the Option-Critic architecture. Firstly, I will provide you some background about this research. Then we will have a look about the details about learning options. Lastly, I will show you some evaluations about this architecture. So as we know, in options, we can assemble a big target into multiple sub-goals such that we can use some reinforced learning to learn and solve these sub-goals. For example, here we have 4 rooms, and assume we start from a random state, and we want to achieve at the G1 point. And a sub-goal here can be the gate between this room. So here we firstly arrive at the sub-goal. Then we can use another policy to achieve at the G1 point. For most existing work, they define some sub-goals, then use the reinforcement learning to solve these sub-goals. But there are 2 primary problems with this kind of solutions. The first one is that it is pretty costly in both data and time consumption with this kind of solution. Another problem is that we need to define this kind of sub-goals by ourselves. And we're wondering if we can find a solution which can find options in the option framework automatically and efficiently. As we know, in Markov decision process, we have a set of states, a set of actions, and a transition action, and a reward function. And we want to find a policy to solve the problems. And we may need to find the value function and the action value function, and also the discounted return. So the policy gradient theory provides us a basic idea how to find an optimal policy with the stochastic gradient descent. So here we have the partial derivative between the discounted return and the theta. And here mu is the discounted weighting of the state along the trajectories starting from S0, and the Q pi is the action value function for the given policy pi theta. So firstly, we are wondering if we can use a cylinder manipulation in option framework to find options similar as this kind of theorem. So firstly, let's define the option framework. In the option framework, we have some options, and each option can be defined as omega, which is made up of 3 components: the I omega, pi omega, and the beta omega. And the I omega is the initial state, and pi omega is the option intro policy, and beta omega is a termination function. Here I will provide you a basic example. For example, we have a robot. We can write it as R, and this robot has a set limit, and let's assume it has this kind of set range. And we want to park this robot in the charger such that this robot can charge itself. In other words, only when this robot arrives at this range, it can find the charger, and we can define the option for the charging for this robot as omega. And here we have our I omega as this range. And we can use a pi omega to park this robot to the charger. In other words, when we can evaluate the termination function omega, beta omega for C equal to 1, because once the robot arrives at the charger, this option will terminate. And another problem is that sometimes the policy is not so good enough, and the robot will go out of the option. And at that time, the beta omega will evaluate it to terminate as well because the I is out of the initial state. So we also define pi omega theta as an intro option policy of omega parameterized by theta, and the beta omega was theta as termination function of omega parameterized by theta. And also we define the option value function as q omega, which is the expectation of the option action value. And the option action value can be calculated by the reward plus the discounted expectation of the option value upon arrival. And there is a condition, and we can write U for option value function upon arrival. If the next state is the termination state, the option value function upon arrival will equal to the value of the next state. Otherwise, it will be equal to the option value of the next state. And with this definition, we can do some mathematical computation, and we get two primary results. The first one is the intro option policy gradient theory. And here it provides the gradient of the option value function with respect to theta. And the mu function here is the discount weighting of the state option pairs along the trajectory start from S0 and omega 0. And another theorem we get here is the termination gradient theorem, which provides us the gradient of the option value function upon arrival with respect to theta. And here it is the mu is a bit different because it provides the weighting of the state option pair along the trajectory from S1 omega 0, and the previous one is S0 omega 0. And also we have the advantage function in this equation, and the value of advantage function can be calculated by the difference between the value option value function and the value function for the next state. So with previous two theories, we can build an architecture and an algorithm. We name it as Option-Critic architecture. And the basic idea here is that for an initial state S0, we will use a policy over option to pick a suitable option for the current state. Then we can apply the option and intro option policy to select a suitable action for the state. And the agent can interact with the environment, and then we will evaluate the options and get new QU function. Also, we want to update the option based on the result of previous two theory. And lastly, after taking this action, we need to evaluate the termination of the next state. If the next state is not a terminated state, we can continue using this option to take another action. Otherwise, the option will be terminated, and we need to use the policy over option to select a new option for this new state. And this kind of process will be repeated. And then we can use our architecture to do some application. And the first evaluation is in the four-room domains. As you can see here, we compare the architecture with two other kind of reinforcement learning methods. And in the first 1,000 episodes, our solution converged to the goal a bit slower than the other two reinforcement learning. However, once there is a standard change of the goal, for example, we move the goal from one place to another place, our solution can can converge to the goal much faster than the other solutions. As we introduced at the beginning of this presentation, a sub-goal, the option can be a suitable sub-goal in a domain. So in a four-room domain, a suitable sub-goal can be the gate between two rooms. And this graph shows the termination probability distribution of in the four options. And the lighter points means the option has higher probability to terminate in that point. So as you can see, in these four options, most of the termination points are near around the gate between two rooms. And that fits our intuition. Another experiment was played in the P-ball game. And the basic idea about this game is that you start from the top left side, and you want to control the ball from the top left side to the bottom right side in the maze. And the shape of this maze can be randomly created. And here we evaluated for three kinds of options. And there are two options, three options, and four options. As you can see, with the number of option increasement, the performance can be increased as well. Lastly, we evaluate the architecture in the arcade learning environment. So actually, we extend deep learning neural network from another paper, and we keep the shape of the first three layers and add another layer in the neural network with the architecture. And in the experiment, we find a problem is that if we do not add any baseline for the Q omega function, it is pretty easy for the intro option policy to be deterministic and quickly, and that's not good for our exploration. So we add some baseline for the agent, for the option value function, and let's make the intro option policy to be less deterministic. And this flow graph shows the performance of our new neural network in 4 games. And generally, the new neural network can find the goal in 200 epicores. And we also find a pretty interesting stuff is that for the C-Quest game, you have 2 options to control the ship up and down to get rid of collision with other ships. And if we chose 2 options, then the neural network can create 2 separate options. One is for controlling the ship going up, and another one is for controlling the ship going down. And to be concluded, this paper proved 2 primary theorems in the option framework and raised the option-critic framework and architecture and algorithm. Lastly, we evaluate the option-critic architecture in different kind of domains. And this is the reference for this paper. Thanks.